We know how to find the area of a rectangle. We know how to find the area of a square, a triangle, a trapezoid, a lot of polygons, a circle, an ellipse. But what if we want to find the area of a region that just has curvy sides that aren't specifically of those types? Well, that's a question that mathematicians had for a very long time, which actually precipitated the origins of calculus. In this video, we're going to look at how to find the exact area of a plane region caught between a non-negative continuous function and the x-axis over a closed interval. Once we get that, we'll also later in other videos attach that idea to how we could find it as application using our definite integrals, and then get some other extensions with areas of other types of regions. So this is just the start in the foundation, but it also builds on the ways of approximating the areas that we've already done. Now, in earlier videos, I approximated the area of a plane region with a specific number of subintervals, and I've attached the link to that video in the description of this one, if that's what you've been asked to do, just approximate it. I also attached to this one a video that talked about the notation that we're going to use, as well as just working with summations and then working with the limit of a summation of a quantity. If you aren't comfortable with that stage of this video and want to focus a little bit more of what's going on with those, then I invite you to watch the videos as a background to help you get better at what we're going to do here. But our focus here, again, is to find the area using the limit definition. Let's get started. So let f be a continuous and non-negative function on a closed interval from a to b. So continuous, remember, you can draw it without picking up your pencil, and actually it had specific definition of continuity in earlier work in our calculus. Non-negative means that its graph is on or above the x-axis. So the graph of your function cannot go below the x-axis over this interval for our value to come out as the area. And then our interval has to be a closed interval. It has to include the endpoints. Now the area bounded by the function, the x-axis, and the vertical lines at x equal a and x equal b is defined to be. So this is a definition that you're going to want to write down in your notes. You want to make sure that you readily have that available whenever you're trying to find the area of a plane region in using the limit definition. Okay, so our area is equal to the limit as n approaches infinity of the summation I equal 1 to n of f of c sub I times delta x. So in that video with the area approximation, we did the area approximation from the area of the rectangles added up, and our f of c sub I is our height of our rectangle, and our delta x is our width. So length times width gives you the area of the rectangle, and then we're adding up these rectangle areas. This time, however, with our equal width, we are taking the limit as the number of sub-rectangles or the number of sub-intervals approaches infinity. So we're packing infinitely many of these very thin little sub-intervals, making our little sub-rectangles, and so they conform to the curve, and that's what gives us out our actual area. Now, if you were going to do this where the widths of the sub-intervals are different, not the same throughout, then this definition would look different, and you would have to seek out the largest width and keep letting that get smaller. We are in here specifically taking our c sub I to be any x in the ith subinterval, but our delta x to be b minus a over n. They are going to be equally width. So packing infinitely many of those equally width ones takes care of what we need to do. Now also recall that the summation I equal 1 to n of a number is just the number times that n. The summation I equal 1 to n of I, if I, instead of adding them up all individually, wanted to just jump to what that total is, I can get it by taking n times n plus 1 over 2. And the summation I equal 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 all over 6. Now, I just listed here the ones that we'll need for this problem. There are a lot of other summations. If you had a polynomial function that's degree is higher than what we're doing, you could reference those just like for Googling summation formulas and that sort of thing. Working with these and manipulating them, again, there is a video that I've posted on that, which I'll link also in the description. So at any point in this work, if there's something that you don't have the background in or don't have it as strong as you would like to be able to follow along with what we're doing here, go back and watch some of those earlier videos that are linked in this description so you can see more in depth what's happening at that step. All right, so now let's look at an example of how to do this. So this says find the area, not an approximation to the area, but find the actual area enclosed by f of x equals x squared plus 1 on this closed interval from 1 to 3. And I'm going to do this by the limit definition because that's what this video is all about. Again, there are other ways that we'll learn further down the road applying the topic of our definite integrals, but for now, we are just going to use the limit definition to find it. Now, when we're doing this, there's a few steps we can kind of get to set it up and then be ready to go. So first, you want to find your delta x. And delta x is b minus a over n. So I'm going to write that again here, b minus a over n, to just kind of get a couple more times where we say it. And then remember that a is the start of your interval and b is the end of the interval. Since our question is over the interval from 1 to 3, our a is 1 and our b is 3. So our delta x is 3 minus 1 over n, or 2 over n. Now, what about our c sub I? Well, c sub I could be any x value in the subinterval, and I always like to use the right endpoint because it makes more sense to me to have an easier time with the notation with that. See, the right endpoint, let's just draw a little sketch of our situation here. F of x is x squared plus 1. So we get our parabola like this. It's on the interval from x equal 1 to x equal 3. So x equals 1 to x equals 3. Draw your vertical lines, and that one I'm going to extend my a little bit more to hit it. And that region is caught between the curve of the x-axis over that interval. So this enclosed spot, this part of it is the area that we want to find. Now in this, as I break this up into subintervals, my right endpoint is what my right finger would be pointing to. So when I start with my a and add a delta x, that would be a plus delta x for the right endpoint of my first subinterval. And it'll be a plus 2 delta x for the right endpoint of my second subinterval. And it'll be a plus 3 delta x for the right endpoint of my third subinterval. So if I use the right endpoints, the coefficient in front of my delta x matches the subscript of the subinterval I'm working on. So that's why I always choose my c sub I to be the right endpoint, so I can then use the notation a plus I delta x for my c sub I in the work for this application. Now for our particular question, that means my c sub I is, well, what's a? A is 1. Plus I, and what's delta x? Delta x is 2 over n. And I want to think of that as an I over 1 times the 2 over n. So I want to think of that as 2I over n. So my c sub I is 1 plus 2I over n. Now this I is the index of summation. It has nothing to do with the complex number I. It's just our index of summation. So you need to just keep it in context. Sometimes you'll see people write it with a index of summation of like j. So they say j equal 1 to n of j, or it could be k. So whatever the index is, you just use that part of it. All right, so now we want to find the area, and the area is this formula, only when we get to this part of it, we're going to use the specifics of our question. Okay, so our area is equal to the limit as n approaches infinity of the summation I equals 1 to n. So I'm just writing exactly what's here. Now this part, f of c sub I. My function is the function for my question, and my c sub I is the c sub I we got in step 2 for our expression for our specifics of our problem. So I'm going to put it in brackets because my function has more than one term. I'm going to plug this 1 plus 2I over n in for the x's. That's what f of c sub I means. It means put this in through your function in the x spots. So this is going to be 1 plus 2I over n squared plus 1. Okay, so that's my f of c sub I for this problem. But then I also need to multiply it by the width of the rectangle as well. So multiply it by my delta x. And my delta x for this problem is 2 over n. All right, now if you have to stop the video just to look at this for a minute to make sure that you see where everything comes from, certainly you'll want to do that. But now we're going to keep going and simplify our expression as much as we can to be able to do our limit. So now what we need to do here with our summation, limit as n approaches infinity, is I equal 1 to n. To multiply out this binomial and then combine our like terms in here. And then there are some things that we can do to kind of help with ease our calculations as we go. So we are going to take 1 plus 2I over n times itself. So think 1 plus 2I over n times 1 plus 2I over n. So that's 1 plus 2I over n plus another 2I over n plus 4I squared over n squared. And remember, this is just the index of summation. It's nothing at all with the complex number. So now when I see that I have like terms with a common denominator, 2I over n plus another 2I over n is 4I over n. So that's 1 plus 4I over n plus 4I squared over n squared is the multiplying out of that binomial. And then that's still plus 1, and then still times 2 over n. Okay, now let's look at what we can do for our simplification. I do have a 1 plus 1, that'll be a 2 there. And the multiplication of this 2 over n, there's no i's in this. It's attached by multiplication of the rest of what's being in the summation, and the summation's index of summation is I equal 1 to n. The n isn't a variable in your summation, it is in your limit. So this factor of 2 over n, I can bring that in front of the summation, and that still is okay. And then it's equivalent to the previous expression. And then summations can be broken up over addition or subtraction. So the sum of an addition or a subtraction is the addition or subtraction of the sums. So we're going to have our area is equal to the limit as n approaches infinity. I'm going to factor this 2 over n in front of the summation, so it's 2 over n. And then I've got my bracket, and I'm going to take the summation I equal 1 to n of this 1 plus 1 is 2, plus, so that's those taken care of, the summation I equals 1 to n of 4i over n, and then plus the summation I equals 1 to n of 4i squared over n squared. So now when I look at this, I'm not quite where I can use these rules for my summation. I need to, within each of them, see what I can apply. So the summation I equal 1 to n of 2, so you're going to look at this term, then this term, then this term. So this is the summation I equal 1 to n of a number. So I do have a rule for that. In the second term, summation I equal 1 to n of 4 times I over n, well, this 4 factor and this n are not the index that we have in our summation. So this 4 over n can pull out just in front of that summation. It's not the whole thing, just that one. And in this last term, my 4 over n squared can come in front of that summation. So my area is the limit as n approaches infinity of 2 over n times, I'll have my summation I equals 1 to n of 2 plus 4 over n times my summation I equals 1 to n of I, and then plus 4 over n squared times my summation of I equal 1 to n of I squared. Now I can replace the summation of that quantity with the rule that we were remembering from before. So our area is equal to the limit as n approaches infinity of 2 over n times, so summation I equal 1 to n of a number. It starts at 1, ends at n, and it's of a number, so that's just the number times the top out, so 2 times n. Then plus 4 over n times the summation I equal 1 to n of I. So the summation I equal 1 to n of I, that goes out and gets replaced with n times n plus 1 all over 2. Plus 4 over n squared, and the summation I equal 1 to n of I squared, that's going to go out, and we're going to plug in this n times n plus 1 times 2n plus 1 all over 6. So now that's gotten where I've been able to replace the summations with all of their equivalent formulas, and I need to simplify this so that I can take this limiting process of it. So area is equal to the limit as n approaches infinity of 2 over n times, well, this is just 2n, and then plus, in this term, I have a common factor of n that removes and a common factor of 2 that removes. So this common factor of n's will remove, common factor of 2's will remove, and I'll have 2n plus 2. And then plus, and in this multiplication of 4 over n squared times n plus 1 times 2n plus 1 all over 6, I have a common factor of n that'll remove and leave me an n in the denominator, and then a common factor of 2 that'll remove. So I'll have a 2 in the numerator and a 3 in the denominator. So I'm going to have my 2 times that n plus 1 times 2n plus 1, and that's going to be over 3n. I'm going to simplify just a little bit more. We are going to multiply out this binomial and then distribute the 2 through, and then we'll look at our limits. So area is equal to the limit as n approaches infinity of 2 over n times, well, this 2n plus 2n is 4n plus 2 plus, when you multiply out n plus 1 times 2n plus 1, you're going to get 2n squared plus 3n plus 1. And when I take 2n squared plus 3n plus 1 and I multiply a 2 through, I'll have 4n squared plus 6n plus 2 all over my 3n. Let's go ahead now and multiply that 2 over n through each term. So my area is the limit as n approaches infinity of, well, 4n over 1 times 2 over n will just give me 8. Plus 2 over n times 2 is 4 over n. Plus, and then 2 over n times this expression, I'm going to distribute the 2 through, and then my denominators. So that will be 8n squared plus 12n plus 4. And that's all over 3n squared. Now, remembering your limits at infinity, and again, if that's something that you need a little review to, I'll put that link in this description as well. Well, the limit as n approaches infinity of my separate terms, I do term by term limits. Also, a limit as n approaches infinity of a number is just that number. So we have 8 and then plus. The limit as n approaches infinity of a constant numerator divided by going off to infinity denominator, that fraction value goes to 0. So my next term goes to 0 plus, and the limit as n approaches infinity of a polynomial divided by a polynomial when the degree of the polynomials in the numerator and denominators match, that ends up being just your lead coefficient of your numerator divided by the lead coefficient of your denominator. So this is going to end up being a limit of 8/3. So then when I get a common denominator of 3, I will have 24/3 plus 8/3, which is going to give me 32/3. So that is my 32/3 square units of area for this. So when you think about just the mixed number of it, it would be 10 and 2/3 square units. So if you had this graphed very carefully on graph paper and you counted the number of square units enclosed by this region, and of course needing to approximate when it's parts of the square units that are enclosed in it, you would count approximately in here your 10 and 2/3 square units. You could see if you have a reasonable answer or not for your area, and if you did all of this work right for your area by actually comparing it with your enclosed region and seeing that you're in the ballpark. So this would give me the exact area, and then counting the square units enclosed by it would give me my approximate area. So there's a lot that is in the background of information that you need to know in order to follow along with the steps of this process. I will link again in the description of this video all of the ones that I've posted that are the foundation information that you need to use within this. But hopefully you've found it helpful in being able to understand more about how to find the area of an enclosed region using the limit definition.